Hello everyone, Dr. Zia Tahir here. So this video tutorial is about magnification factor versus frequency ratio plot in MATLAB. So highlights of it. So for single degree of freedom spring mass damper system under harmonic force Ft, so F0 cos omega t, that is a forcing function. So when that is a forcing function, so then dynamic amplitude divided by the static amplitude. So that will get a relationship which is called as amplitude ratio, or that is called as magnification factor. So that magnification factor is a function of R and zeta. R is the frequency ratio and zeta is damping ratio. So in this video tutorial, first I'll explain how a function of magnification factor for R and zeta, how that can be written in MATLAB, and then a 2D plot of the magnification factor as shown in figure, and then 3D line plot and 3D surface plot. And in the end, I'll explain relationship like how magnification factor changes with the frequency ratio for various values of zeta. Okay, so first step is I need to write a function. So a function, if R and zeta is given to it, and it can calculate or compute magnification factor. So I need to write function for this expression. So I am using MATLAB 2021, and this layout is the standard one or default three-column layout. So first, I here in the search bar, I'll put function like that, and it will take me to the MATLAB help. So here is a function. So this is a built-in function called function, declare function name, inputs and outputs, and it is a syntax for that. So function outputs is equal to my function, that's the function name, and then several inputs. So like as here is an example to find out average values. So like in here, we need to write function, then define outputs, then equal function name, and then inputs. So here I'll go to like new, okay, and I'll put new function. So either you can use a live function or you can use here in the new live function or simple function. So there are two types here. So I am using a simple function. So what it gave me? It gave me function equal output argument 1, then output argument 2 is equal to untitled, that is function name, and then input argument 1 and input argument 2. So here I have given it like in this one m equal avr. So AR versus FR is the function name. Input are R and zeta. Zeta I am using here Z, and M is a magnification factor. So here I need to write. I have only one output argument, which is M, so I'll use that one only. So that is function M equal AR versus FR. So AR versus FR is the function name. So it should not be same as built-in functions of MATLAB. And R and zeta, these are inputs. So then here untitled 5, summary of this function goes here. So summary of function, I'm writing. So with the comment AR versus VR function to compute amplitude ratio from frequency ratio and damping ratio. Here M is the amplitude ratio or magnification factor, R is the frequency ratio, Z is the damping ratio, and then here because I have only one output argument, so I need to write here the equation. And what is the equation? Equation is M equal 1 over square root 1 minus r squared square plus 2 zeta r square. So I need to write expression here. Now that is expression m is equal to 1 over dot square root 1 minus r dot squared plus 2 r into z squared. So that is a function. So now once that function is being written, I am going to save it with control S. With control S, and it automatically save this function as AR versus FR. So now this function is being saved as AR versus VFR in here in the current folder. So now I have saved it, and the next one I am going to use that function. Next step is plot amplitude ratio versus frequency ratio for various values of damping ratio as 2D line plot, and function built-in function is plot x and y. So for 2D plot, we have the function name plot. So in MATLAB help here, I'll just say plot, and it gives me that option plot 2D, and here is a plot 2D. So 2D line plot, and it's a plot XY. So plot XY, what is that? Create 2D line plot of the data Y versus the corresponding value of X. And if X and Y both vector, they must have the equal length. Okay, the plot function plots y versus x. So I am going to use that function here, but this one is not that simple as we have like in this figure. Is not that simple because here I have to plot uh, various values of theta on the same one. Okay, so usually what is going on? So we first take any certain value of zeta. For that value of zeta and a given value of r, we'll compute magnification factor and then plot it. And then we hold on it. Then the second one, third one, and all that we need to do. So here is a script AR versus FR underscore 2 underscore plot M. So 2D line plot of amplitude ratio of magnification factor versus frequency ratio for different values of damping ratios. Okay. So, and then here M is the magnification factor, R is the frequency ratio from 0 to 2 with an interval of 0.01. Then Z is the damping ratio from 0.2 to 1 with an interval of 1. And for this one, I am going to use a loop. So first, I'll use that 0 colon step, which is 0.01 to n, end. So like as if I do like 1, step 1 to 5. So that is a starting value 1, end value 5. So it will create a column or a row with, so it will create a column like as with the row. So like as a equal to 1, initial value, step size, and final value. So it will create like a row with the values 1, 2, 3, 4, 5. So starting from 1 to 5 with a step size of 1. So that is I have used here. So the first one, what I did is R, I took it from 0 to 3 with an interval of 0.1. Then I'll apply a loop for Z equal 0.02 to 1 with a step size of 0.1. So what this loop is going to do, it takes first value of all values of R, which are defined there, first value of zeta, and by taking all values of R and first value of zeta, it will compute M. So let's say I'll show you here like this one, R, and then Z is just 0.2, and then here it takes each value of R, so all values of R and then zeta, and then it compute magnification. Like as I have R values like 301 R values. So if I plot it, so it is from 0 to 301, and then the magnification factor values for that, it is the same one, the magnification factor values, and then I can plot that R and M. So it will give me this one. This is a curve. Okay, so now what will happen? I am going to apply a loop and then I'm putting that grid on. So it will add a grid on that graph. So like as here you have, and then if I do grid on, so it will add grid on that graph. Here you can see, and then hold on. Hold on means that it will hold it, and then you need to add here figure and then one. If you're not going to put restrict that figure, so it will create like so many figures. Like let's say if I'm not going to put and going to run that function, so what will happen? It will create like like that is a figure 9, figure 8, figure 7. So it will not use all those, or otherwise you need to uncomment that one, and then you will see that it is going to give you like figure 1. So all those figures I'll use that close all to close all those figures, and then you can have like this one. Okay, so it will give you the figure 1. So usually, so you can use here figure as 1. So now, and then if you're going to hold off it, and then it will give you that graph. Okay, so now you need to put axis on that. X label is a frequency ratio, Y label is a magnification factor, title is a magnification factor versus frequency ratio, and then need to put legend as we have started it there, like from the first to end. And if it is too long, so you need to put that 3 dots and then enter, so it will continue the function. So now if like this one, if I run the function, so it gave me that 2D plot, and which one is very much similar to this one. But because I'm not using that point 1, but for point 2, so for point 2, so that is a 2D plot. Now the next step is plot magnification factor or amplitude ratio versus R for various value of zeta as 3D line plot. And syntax for that is, a function for that is plot 3 x, y, and z. So for this one, if I write here in the help plot 3, and then it takes you there 3D plot or line plot. So plot 3 x, y, and z, and here is plot 3 x, y, z, plot coordinates in 3D space. To plot a set of coordinate connected by line segments, specify x value as a vector of same length. So they must be same length. Okay, and to plot multiple set of coordinate on the same set of axes, specify at least one x, y, z as a matrix. And here is an example like time and then sine of t and cos of t, and plot 3 sine, cos, and t. So now here, this is the x-axis, that is the y-axis, and that is z-axis. So this will be x-axis, that will be y-axis, and that is z-axis, and this one is origin for x and y. So here I have already written that function AR versus FR. So now I have here 3D line plot of amplitude ratio or magnification factor versus frequency ratio for different values of damping ratio. So here M is the magnification factor, R is the frequency ratio, Z is damping ratio. And again, I am using here the same script which I have just explained for uh, 2D plot. And what's the difference here? The difference here is because I am going to plot M, R, and zeta. So all those must be of the same length. Like as in the previous one, if I am giving 301 values of R, so it is giving me 301 values of M. But Z is one value. So what we need to do here, I need to produce a, a vector of ones. So ones is a built-in function. Ones is a built-in function which like as ones is a built-in function in MATLAB. So like if I say that 2, so it will create a matrix 2 by 2. And if I say that one row and two columns. It will, sorry, one row and two columns. It will give me a matrix like one row and two column, or otherwise I can say two rows and one column. So two rows and one column. So what I'm going to do here, because here R is a, this one is a row matrix. So I am going to use ones starting like one row, and how many columns? Length R column. So whatever is the length of the R, so R is 301. So if I just copy it here, so it will give me the answer like 301. Okay, so I always try use that whenever I have a script. I use clear on that. So then Z, that Z is a, like as here. So uppercase Z is 10301. So that is a new thing you need to create. You need to create a vector Z of same length of M and R. So then I'll run only that script, and then I'll put X label, Y label, Z, and title on it. So now here is the plot. So that is the plot. Here is the damping ratio. That is the frequency ratio, and then the magnification factor. So now, like as these are the peaks, so with this rotation, I can rotate that. So I can't see that very much clear because the peaks are coming this way. So now I need to rotate, reverse that uh, x-axis. And how is that possible? To reverse that x-axis, so here I have set. So that is a command for it. So set GCA x direction reverse. So it will reverse that x direction. So now here you can see the like the curve with the lower height are here, and then so this way this is a very much good interactive graph. So or like is more visible compared to the previous one. So with this one you can rotate 3D, and then but still is not that much clear. So what I want to rotate that y-axis as well. So how to do that? It's very, very simple. Rotate. Here I have set GCA and reverse it, sorry, reverse y direction, and then this is like it is a much more clear compared to the previous one. So you can see here like this is when zeta is zero point 0.2, and as the value of zeta is going to decrease, so you can see that even at resonance at frequency 1, the uh, the resonance is not that much prominent. So this is how you can plot, and then you can to present in book like on anywhere. So you can just rotate it and see that where it is more visible. Okay, so where you can easily compare the values. Like you can go like this way, but this is standard one. X x-axis, y-axis, and z-axis. So this is how you can plot that uh, magnification factor versus frequency ratio as 3D. Now the next one is plot M versus R for various value of zeta as 3D surface plot. So if you need to surface plot, and then function built-in function for that is surf. And how is that possible? So you can just in the help you put surface, so that is a surface plot. So surface plot, and that is the syntax for that surface xyz create three-dimensional surface plot, which is three-dimensional surface, and it is a solid edge colors with solid face colors. So the function plots the values in matrix Z as heights above grid in XY plane defined by X and Y. So in this one, here is XY plane. So first you need to plot all values of X versus all values of Y. And then for each value, you need to give height at Z. So now, like as, and then here you can, if you put C is a surface color, so I'm going to use that a simpler one, but if you go like which colors you want to give, so you can. use different colors, but I am going to use the very simpler one here. So again, here is I have written a script for that 3D surface plot for amplitude ratio or magnification factor versus that. So this one is not like as you are doing that 3D plot. So it is a different one. So R, I am going to zeta, I am going to put along x-axis, and R, I am going to put along y-axis. So first I need to define it, and then I need to create mesh grid. So what is that mesh grid? So if I'll go in the help here and then mesh grid. If I say mesh grid, so here you have mesh grid. So what the mesh grid do? Like that is a syntax. So if you give it x and y, so it return 2D grid coordinate based on the coordinate contained in x and y. So x is a matrix where each row is a copy of x. X is a matrix where each row is a copy of X, and Y is a matrix where each column is a copy of Y. So the grid represents the coordinate of X and Y as length Y row and length X column. So mesh grid you need to first apply to plot a surface. So here R, and then I'm going to, here I have plotted. So R and Z is like 9 times 61. R, lowercase r is 1 into 61, and then here zeta is 9 times 61. So I have reduced here. Previously, I was using here as like interval of 0.1. So now I'm going to use that interval of 0.05. And then I have that magnification function. So it can calculate all those magnification as 9 times 61. And then here I am going to do surface R, Z, R, and M. So the first which you want to put on x-axis, that will come as first. You put on y-axis, that is come as second, and then Z is M. Okay. So now I am going to plot this one, this function. So here I have the 3D figure. So again, in this 3D figure, what like, because I have started the lower values of zeta here, so all the other stuff is being hiding under this. So I need to reverse that damping ratio. So as I told you, here is a set GCA X direction need to reverse. So now I'll have it like this way. So it is being reversed. And again, the problem is that something is hiding here. So how is that visible? If I am going to reverse that frequency ratio. So frequency ratio is along y-axis. So here, I can simply reverse it. Okay. So now that is a 3D surface plot. And again, something is being uh, missing behind, hiding behind it. But this is how a surface plot looks like. And to get more better results, so you can increase here interval size of zeta, or you can increase interval size of frequency ratio. Let's say if I'm going to increase the here interval size of zeta from zero point 0.1 to 0.05. So let's say here 0.1 to 0.05. Okay, so I'm going to run it, and then this one is much clearer. Or even you can reduce that one from 0.05 to 0.025 to get more better graph. Okay, and then here you can rotate it 3D, and it is very much clear now. So you can see it. It looks pretty cool in surface compared to 3 3D line. And if you want to add a color bar here, so color bar is going to represent the minimum value is here, and the maximum value of 2.5 is at that point. So this is how a 3D plot you can 3D surface plot you can plot. And if I'll do as I did previously, like for R, a step size of 0.1. So what will happen in that way? So you can see that on vertical this y-axis, so the things are very dense. Okay, so like as here, so the grid size, so due to that black color grid lines, so the figure doesn't look very nice. And for this one, let's say I'm going back to putting as 0.25. Okay, and then see, so it is, this one is pretty much better compared to the previous one. Okay, so this is how you can plot 3D surface plot. Last one, mm, like like what is the use of this graph? So I am going to explain from surface plot. So here we have surface plot. So that is in the standard one in 3D. And like as when we have a system subjected to harmonic force, so then our prime purpose is to avoid resonance. Because what will happen at resonance, amplitude of vibration that becomes infinitely large. Like as here you can see the amplitude of uh, vibration at resonance is very high. So the first one what we can do is amplitude of vibration is very high. So we need to avoid resonance. Okay, but in some cases, if resonance, we can't avoid resonance, so then what is the solution for that? The solution is to introduce damping. So like as if I plot this one, instead of that, I'll start with zero point 0.1 and I'll run it. So you can see that for a very low value of damping ratio, for a very low value of damping ratio, so here the maximum value is 5. So at resonance, for a very low value of damping ratio, which is 0.01, here you can see at zero point 0.1, so the value is somehow where 5. So which means that dynamic amplitude is 5 times more than the static amplitude. And even if there is no resonance, so then we will have this one going very far away, like as it is like at resonance, if there is no damping, so amplitude of vibration becomes infinite. So how we can control that one? So if we need to first avoid resonance, if we can't avoid resonance, then we need to reduce the amplitude of vibration at resonance by introducing damping. Like as if zero point 0.1 damping is being introduced, and at resonance, so the amplitude of vibration is, our magnification factor is somehow like is not exactly 5, but somehow around 5. Okay, so then we can use damping to introduce to reduce magnification factor. Let's say I'm going to run it again. So now, and then what the surface plot is going to tell me, this surface plot is going to tell me that as damping ratio is going to increase, the amplitude of vibration is going to decrease. Like as the blue color is representing a minimum value, and that yellow color is going to represent that maximum value. Okay, and as you are going to increase the value of zeta damping ratio, so like as when the amplitude damping ratio is somewhere, when that it is somewhere around 1 at resonance, so the amplitude of vibration is just half of is half. So if resonance cannot be avoided, so then by introducing damping, the amplitude of vibration can be reduced. Okay, so like as what is the optimum value we can get from there? So like we are not going to increase it, so, like as here you can see. So magnification factor for few values of, here you can see, like let me, yes. So like somewhere around zero point 0.6. Okay, so if the damping ratio is around 0.6, the amplitude of vibration or magnification factor is 1. So from here I can see that around zero point 0.5 or around zero point 0.6, if amplitude damping ratio is being introduced, so then we can get magnification factor as 1. But introducing damping, a higher value of damping, that create other problems for structure. And what are the other problems? Like more damping is being applied, so more energy is being wasted from the system. And again, a higher value of damping is not again advisable. So this is a video like how to create a plot and then how to create a function and then how to create plots. So thank you very much for watching. Thank you very much for watching again. And please subscribe my channel for more videos on vibration analysis and on finite element analysis.